This is session number 3 of the chapter Some Basic Concepts of Chemistry. In the previous session, I discussed about accuracy and precision, significant figures, dimensional analysis, and law of chemical combinations. Now in this class, I am going to talk about the work of John Dalton. So John Dalton is the first scientist who talked about the atom, and he gave the assumptions or postulates of atom, and the theory we call it as Dalton's atomic theory. So now in case of Dalton's atomic theory, he considers the chemical reactions, the 5 different laws of combination, and based on that he gave some postulates or assumptions, and I am going to discuss that one by one. So the first one postulate you see, matter consists of indivisible atoms. So we know that the constituent particles present in matter are atoms and molecules, the non-living particles you can say. So the matter consists of indivisible atoms. The atoms which are present, they are invisible and indivisible also. You cannot see with the naked eye, you cannot divide that also here. So that is the first postulate given by John Dalton, that is the matter consists of indivisible and invisible atoms. The second one is all atoms of a given element are identical and different from those of other elements here. So let me explain with example here. All atoms of a given element are identical. So let us assume I consider Na. This is symbol of the element sodium. We know that elements are represented by symbols. If you consider sodium as an example, and if you consider oxygen as an example here, so these two are two different elements if you consider. So if you consider the element sodium, okay, so inside the sodium element we have sodium atoms only. Inside oxygen element we have oxygen atoms only, okay, and inside sodium we have sodium elements. All are same, therefore I use the word all are identical. So all the atoms of a given element are identical, they are same with respect to physical and chemical nature. And when you compare the atoms of sodium and atoms of oxygen, so if you consider these two elements, so sodium atom is different as well as oxygen atom is different. The properties are going to differ when you compare sodium atom and oxygen atom here. So in the one element all the atoms are identical, but if you compare the atoms of the another element, they are not identical, they are different with respect to each other. That's why the second postulate says all atoms of given element are identical and they are different from those of other elements. Next one you just look over, compounds are formed by when atoms of different elements combine in a fixed ratio. And if you just recall the law of definite proportions, okay, and what I explained, if you consider one compound as water, the ratio of hydrogen and oxygen, they are in the ratio 1:8. If you calculate the atomic mass or molecular mass of this water and hydrogen and oxygen, you are going to get the ratio of hydrogen and oxygen in the ratio 1:8. Okay, so water is a compound. So remember, in compound we have more than one elements here. In this case we have two elements, one is hydrogen and one more is oxygen, and they used to combine and you are going to get a compound. But remember, according to law of definite proportion, it says that the element has to be combined in a fixed ratio. In this example the ratio is 1:8. So the statement is compounds are formed when atoms of different elements combine in a fixed ratio. And then you may think, what happens when the atoms of same elements will combine? When the atoms of same elements will combine, we are going to get a molecule. Okay, when oxygen combines with oxygen, and you are going to get O2, oxygen atom, oxygen molecule you are going to get. When two different elements combine, then you are going to get a compound. But remember, they has to combine with a fixed ratio, and here is the example what I have given. The fourth one is the chemical reaction involves reorganization of atoms. We know that one, if we consider any chemical reaction, there is a chemical change, and chemical change is represented by chemical equation, so that the atoms they organize in a proper manner and you are going to get a new product in the case of a chemical reaction. So I can say chemical reactions involve reorganization of atoms. The last one is very simple, that is atoms are neither created nor destroyed in a chemical reaction. And if you just recall that, this is almost as same as the law of conservation of mass. Okay, and I explained that already in the previous session. That is, if you consider a chemical reaction, okay, the molecular mass of the reactants and the molecular mass of the product will be same if you consider a balanced chemical reaction, and that is based on law of conservation of mass. Since the molecular mass will be same, then one can easily guess that the atoms, okay, and atoms, there is no creation or no destruction of the atoms in a chemical reaction, only there is a reorganization so that a new compound is going to be formed. And that is about the last postulates of Dalton's atomic theory. Remember, Dalton's atomic theory is the first theory that explains the nature of atomic model. Of course, we have some other theories that we will discuss in some other chapters here, but remember, Dalton's theory is the first theory, and that is explained by John Dalton, actually the name of scientist, and he explains by considering very simple, general and fundamental concepts about the chemical reaction. So that is about the postulates of Dalton's atomic theory. Now we'll discuss about atom only. So now see, atoms are indivisible, invisible, we know. Atoms cannot exist independently also, we know. And we know one more concept, that is elements are always represented by symbol. Okay, first we will see the basic and we'll move to the concept here. If you consider any element, in general we represent the symbol of an element X in general. Okay, and subscript we write Z, superscript we write A. Okay, this is actually how we represent the elements in general. X is the symbol of an element, and subscript below what we write, subscript, that is Z, and remember Z stands for atomic number, and superscript, the above what we write, that is A, that stands for atomic mass here. So Z is atomic number and A is atomic mass. So what is atomic number and what is atomic mass, we'll try to know, and later we'll see actually what actually atomic mass and molecular mass I am going to discuss. Remember, atom consists of 3 subatomic particles. The particles which are present inside the atom we call it as subatomic particles. There are 3, and I hope you know: protons, neutrons and electrons. Protons and neutrons are present inside the atom, whereas electrons used to revolve around the atom. Okay, and if you calculate the total number of protons only, that constitutes atomic number. If you calculate the total number of protons as well as neutrons, that constitutes the atomic mass or mass number, you can say. So in simple, Z is nothing but atomic number, and atomic number is the number of protons. A is nothing but atomic mass is nothing but number of protons and number of neutrons. And one more thing you try to remember, in a atom, it is neutral, we know, the number of protons is always equals to number of electrons here. So that is the concept about the atomic number and the atomic mass. Okay, and now the question arises, atom is very very small, we know. Then the question arises, how we can calculate the mass of that? How we can calculate the mass of protons, neutrons, electrons that constitutes the entire atom? Okay, so in recent days we have one technique that we call it as mass spectroscopy. So using a mass spectroscopy, nowadays we can calculate accurately the atomic mass of an atom. But in the olden days, okay, and it was not possible to have a mass spectroscopy, and they used one different method. And what is that method? They considered hydrogen, and we know that one hydrogen is the lightest element, so they considered hydrogen as a standard, and the other elements mass they started comparing with the hydrogen, and they used to imagine and they used to guess what would be the atomic mass of the new element when compared to the atomic mass of the hydrogen. This was the method used by a scientist in olden days, but now we have a mass spectroscopy, I told you, and the alternative to that is nowadays we consider carbon 12 as a standard. Carbon has isotopes, okay, and isotopes are nothing but elements which has same atomic number but different atomic mass. You try to know, if you consider some elements, atomic number is same and atomic mass is different, and that we call it as isotope. So carbon has isotopes, carbon 12, carbon 13, carbon 14. So these are the isotopes of carbon, whereas carbon 12 is abundant isotope of carbon, you can say. So here we consider carbon 12 as a standard. So carbon 12 as a standard, and if a new element or new atom we have, and we are supposed to calculate the mass of the new element or atom when we are going to compare with the carbon 12. So that is how now we are going to calculate what actually the atomic mass as considering carbon 12 as a standard. In the olden days we used to consider hydrogen, since it is the lightest element, that is considered as a standard, but recent days we have the instrumental technique that we call it as a mass spectroscopy. Then question arises, what actually the atomic mass in terms of recent days? So atomic mass we'll see. So atomic mass, it can be represented in two different manner. One is AMU. AMU stands for atomic mass unit. Remember, AMU stands for atomic mass unit. Recent days we use one more, that is small u. Remember, small u stands for unified mass. Atomic mass unit and small u stands for unified mass here. So in general we write grams, that is nothing but that indicates the mass, okay, but if we calculate atomic mass we considered AMU, atomic mass unit, and recent days we are using small u, that stands for unified mass. Now you remember AMU as well as unified mass, that is same, okay, and in general, in common we write that in terms of grams here. So now we'll see what actually the meaning of atomic mass. The statement I have written, mass exactly equal to 1/12 the mass of one atom of carbon 12 isotope. That is the definition of atomic mass. Okay, so now see, here I used carbon 12 isotope. I told you what is the reason behind that. That is a standard, and keeping carbon 12 as a standard, we compare the masses of other elements or atoms here. So carbon 12 isotope is a standard here, and if you consider one atom of carbon 12, and if you take 1/12 of the mass, 1 divided by 12th of the mass, since carbon 12 we considered 1/12 of the atomic mass, how many grams we are going to get, and that same amount of the mass, and we call it as what actually atomic mass here. Okay, so try to know, we have to consider carbon 12 isotope as a standard. We have to consider one atom of that, and we need to consider 1/12 of the mass of carbon 12, and that mass we call it as atomic mass here. So therefore the statement is mass exactly equal to 1/12 the mass of one atom of carbon 12 isotope, and that we call it as atomic mass. And now, using mass spectroscopy, if you calculate what would be the value, remember 1 AMU, atomic mass unit, the value will be 1.6 into 10 raised to minus 24 grams. So that is the actually one atomic mass unit value in terms of grams. I told you can represent it by U also, and U stands for unified mass here. Okay, and that is about the concept called atomic mass. And now I am going to talk about molecular mass. As the name indicates, if we have atom and we say it as atomic mass, if we have a molecule and we have to call it as molecular mass here. Okay, atomic mass is for atoms, whereas the molecular mass is for molecules here. Atoms combine, you are going to get a molecule, we know that. So how to define molecular mass? Okay, known concept here, sum of atomic masses of all elements. We know that one molecule is made up of elements, more than one elements, and if you calculate the atomic mass, Okay, and if you go on adding the atomic masses of each and every element present in that particular compound or a molecule, and that we call it as a molecular mass sum of, that is the addition. We have to add the atomic masses of different elements here, and then we are going to get what actually the molecular mass. Okay, so now with examples we'll see how to calculate the molecular mass. Okay, so now I am going to talk about the molecular mass. Molecular mass of methane, that is CH4. We'll see how to calculate. CH4 stands for methane, that is alkane, that is hydrocarbon, we know. So what would be the molecular mass of this? So remember, if we have atom and we use the carbon 12 isotope, and this is the standard, we calculate in that manner. Atomic mass is calculated by mass spectroscopy, we know. But molecular mass, how to calculate that? I told you that you need to know the atomic masses of the elements involved, and you have to add that. Okay, so now see, in case of methane, that is CH4, what are the different elements we have? One is carbon and one is hydrogen. So remember, we need to add atomic mass, isn't it? So carbon, okay, so carbon atomic mass is 12. Okay, if you know the basics of modern periodic table, you will be knowing that one, which is atomic number and which is atomic mass, and frequently used elements, atomic number, atomic mass, you should know. Sometimes in the examination they will mention that also here. Carbon atomic number is 6, whereas atomic mass is 12. So carbon I am going to write 12. Sum of, since we are supposed to add that one. The one more element what we have, that is the hydrogen. So what is the hydrogen? Hydrogen atomic mass, that will be 1. But how many hydrogens we have here? Here we have 4 hydrogens here, 4 hydrogen, and we need to add that one. So what you are going to get? You are going to get, what is that? 16 you are going to get. So 16 is a molecular mass of methane. Okay, and here if you write grams, that is also right, and you can write AMU, you can write U also, all of the different methods of representing. Okay, similarly we'll see what would be the molecular mass of, one more example I am going to consider, H2O, that is the water. Okay, two elements are hydrogen and oxygen. So hydrogen atomic mass will be 1, but how many hydrogens are there? 2 hydrogens are there. We have to add that plus one more element is oxygen. Oxygen atomic mass, atomic number is 8, then atomic mass will be 16 here, and 2 plus 16 we are going to 18 grams or 18 AMU will be the molecular mass of water. So now I am going to consider one more example, that will be sodium chloride. Okay, and sodium chloride is a solid in state, we know. Okay, and if you consider sodium chloride, and now we'll see what would be the molecular mass of sodium chloride, and just you see the Na, what is that? Sodium, and what would be the atomic number of sodium? Atomic number of sodium is 11, and atomic mass is 23, and Cl, which belongs to halogen, and Cl atomic number is 17, whereas atomic mass is 35.5. okay, and now we'll calculate what would be the mass of this NaCl, and here I am going to use one more, that is formal mass of sodium chloride. Okay, and now sodium, it is 23, we know. Okay, and one more is Cl, that is 35.5, and if you calculate that, and 23 plus 35.5, you will be getting 58.5, and 58.5 grams or atomic mass unit, that would be the formal mass of sodium chloride. Okay, so what would be the meaning of formula mass? Okay, so formula mass of sodium chloride, here I have not used the word called molecular mass, I use the word called formular mass. Okay, and what actually the meaning stands for? Remember, sodium chloride is a solid in state. Okay, and one sodium, if you carefully observe the structure of that, the crystal structure, one sodium is surrounded by 6 Cl minus ions, and one chlorine is surrounded by 6 Na plus ions. Because of that, instead of molecular mass, we are going to use formular mass of NaCl, and that will be, what is that? 58.5, and this is how we calculate the molecular mass of compound, and similarly we know that one, how we can calculate the atomic mass of atoms and molecular mass of molecules. Now we'll see mole concept. So mole, I hope you know, this is one among 7 basic units, and mole is to be used to calculate the amount of matter present in a substance. The amount of substance, amount of matter can be measured by a unit, we call it as mole. So what is the actual meaning of mole? I told you already, we consider carbon 12 as the standard. So if you consider carbon 12 isotope, and if you consider 12 grams of carbon 12 isotopes, and how many particles are there, and if you count that, and that will be the meaning of mole, that is amount of matter present in a substance. The amount of substance that contains as many particles as the atoms in 12 grams of carbon 12 isotopes. So that indicates, that count, that measurement indicates the meaning of mole, that is nothing but the amount of matter present in a substance. And here this mole can be represented in a different manner. The mole I can represent in terms of mass, okay, in terms of grams I can represent, and one more is the mole can be represented in terms of particles also. So particles, that may be atoms or molecules, and mole concept that can be represented in terms of volume also. So 3 different representations of mole. If you have a 1 mole of any substance, and we can measure or we can write in terms of 3 different manner. One is mass, one more is particle, and one more is volume. So 3 different ways of writing we have. So in general I am going to give example, and later we will see one particular example for that. Okay, and here before moving with the how many mass we have and how many particles we have and what would be the volume of a given 1 mole of a substance, and you need to know, and how many atoms or how many particles are present in 12 grams of carbon 12 isotopes, and that is measured by a number, and that we call it as Avogadro's number. So Avogadro, the name of a scientist, Avogadro's number, and this value will be fixed and it is a constant, and the value is 6.022 into 10 raised to 23 particles per mole. So what is the meaning of that one? If you consider 1 mole of particle, or you can say if you consider 12 grams of carbon 12 isotopes, so these many atoms or these many particles will be present. Okay, so what is the exact value? 6.022 into 10 raised to 23. You can imagine how big this number is, and this much amount of particles or atoms will be present in 12 grams of carbon 12 isotopes, and if you compare the same quantity in the any one more substance, and that will be the same number, that is 6.022 into 10 raised to 23 particles per mole, and this number or this value we call it as Avogadro's number, that is related to mole concept. So now we'll see that. So here what is the value of 1 mole? This is in terms of mass. What would be the value of 1 mole in terms of particle? Value of 1 mole in terms of volume. I told you already, mass, particles and volume. So gram atomic mass, gram molecular mass, in terms of mass we are measuring. Here second one is in terms of particle. Particle, that may be atoms or molecule. If we have an atom, we have atoms. If we have a molecule, then you are going to see how many molecules will be present, element and compound you can say. If it is in terms of volume, we may consider in terms of liters, or you may consider in terms of milliliters. These are the standard values. Okay, so what this, the first one stands for, 1 mole of any substance. In general, this is 1 mole of any substance is equals to gram atomic mass if the original substance is atom, and gram molar mass if the original substance is a molecule. So try to know, almost similar term I used, molecular mass, formula mass, and this is a molar mass. In the previous example I discussed molecular mass, sum of the atomic masses, and in the example of sodium chloride I said that is formula mass, because that is not discrete, or I can say infinite number of Na plus and Cl minus you are going to get. So in that case I use the word called formula mass, and here I am going to use molar mass. So the mass of 1 mole of a substance in gram if you write, and that we call it as a molar mass. Mass of 1 mole of substance in terms of grams we use the term called molecular mass. So if it is atom, atomic mass; if it is molecule, what we can say, molar mass here. So 1 mole is equals to gram atomic mass or gram molecular mass, depending upon whether we have an element or a compound, whether we are going to talk about atom or molecule. So out of these two, you are going to consider that is in terms of mass. Okay, and now we'll see the next one, that is in terms of particle. 1 mole of any substance is equals to this number, that is Avogadro's number, 6.022 into 10⁻³ atoms or molecules here. Again it is, if it is element, we have to say atoms; if it is a compound, we have to say molecule. That depends on the given condition. So atoms, or we can say molecules. In terms of volume, the value is fixed, that is 1 mole of any substance, it has the 22.4 liters. And I hope you know, liter you can use one more unit, that is the dm cube. For milliliters, you can use one more unit. What is that? Cm cube. I told that one. And I told the relation also. That is the 1 liter is equals to 1000 milliliters. Similarly, 1 dm cube is equals to 1000 cm cube. So if we consider 22.4 liters, and in terms of milliliters, 22,400 milliliters or cm cube you are going to get. And again, that depends on the given problem, whether we have in the form of liters or in the form of milliliters we have. So this is the way how we calculate the amount of matter present in a substance in terms of mole, that too in terms of mass, particle, and one more is volume. So this is the fixed one, and this is the fixed value you need to remember. Okay, and if we know this in general, and now we can apply it for n kind of example. So now I will apply it for one example. Okay, so now we'll say I am going to apply it for the example. The example I am going to consider is water. Okay, so now I am going to write here 1 mole of water contains. So 1 mole of water in terms of mass I will write, in terms of particle I will write, in terms of volume I am going to write here. 1 mole of water in terms of mass. In terms of mass, so again question arises, we have two chances here. Either you should go for gram atomic mass, one more is gram molecular mass. Since H2O is a compound, it is a molecule, therefore you need to consider gram molecular mass or gram molar mass. What is the molecular mass or molar mass of water? We calculated that, and I hope you remember that will be 18. So 18 grams I am going to write here. So 18 grams. So I have not considered atomic mass because this is not atom, this is the compound. Therefore gram molecular mass I considered, therefore 18 grams. So what is the meaning of that one? 1 mole of water contains 18 grams. This is in terms of mass. Similarly, what about 1 mole of water in terms of particles? In terms of particles, you may consider atoms or molecules. The value is fixed, 6.022 into 10⁻23 molecules. Since it is a compound, and you are going to consider what actually? Molecules here. So out of these two, atoms or molecules, I am going to consider molecules. One more in terms of volume, that is 1 mole of water contains, in terms of liter, 22.4 liters, or in terms of milliliters, 22,400 milliliters, or dm cube and cm cube we can write. This is how you are supposed to apply the same principle for n kind of atoms or molecules, and that's why this is how we have to remember. So first we remember this in general, in terms of mass, in terms of particles, in terms of volume. And if you know this one, and you can write any kind of examples like that. But remember, the number of atoms or molecules in general, particles will be fixed. There is no variation in the Avogadro's number. That is fixed always if it is 1 mole. And the third one, that is volume, whether it may be in terms of liter or milliliter, that is also fixed if it is 1 mole. If it is 2 mole, and we need to multiply this by 2. If it is 2 mole, and we need to multiply this by 2. But the first one, what is that? In terms of mass, that depends on the given compound what we have. Okay, let me consider one more very simple example, and we will explain that one. Since in terms of particle and one more will be, the volume will be same, we will see that one mole. So now let me ask you one question. What is the value of 1 mole of carbon dioxide in terms of mass? 1 mole of water 18 grams, I told you. Similarly, 1 mole of carbon dioxide. So 1 mole of carbon dioxide is a compound, and therefore you need to consider gram molecular mass. What would be the gram molecular mass of carbon dioxide? And if you calculate, you are going to get 44. Ammonia 17 you are going to get. Methane you are going to get 16. This is how the mass will depend on the given substance what we have, whereas the number of atoms or particles or volume will be the same thing. And one more thing is, 1 mole can be related with these three: mass, particle and volume. Okay, and if you get any kind of problem based on that, and they used to give any two, they may consider mass and particle, or particle and volume, they consider any two. So based on that, we are supposed to write the ratio, and we are supposed to calculate the problems based on that. And for such kind of problems, I will give you one example, and based on that you can consider. So let me consider methane, CH4, combustion of methane, oxidation of methane, O2, and I hope you remember, if any hydrocarbon if you consider, and that undergoes combustion or oxidation, the two products are fixed, that is CO2 and H2O, and we need to balance that one, isn't it? So hydrogen, 4 hydrogens we have in the left hand side, right hand side we have only 2 hydrogens. I use the coefficient term, therefore 2H2 I am going to consider. So oxygen in the left hand side is 2, and here it is 2 oxygen and 2 oxygen, totally 4. I am going to write 2 here, and that's we call it as balanced chemical equation. We have to consider balanced chemical equation to follow the law of conservation of mass. I hope you know how to balance the equations and all these things. Balancing equation is nothing but, in simple I can say, number of atoms of elements in the reactant side and in the product side should be same. That we call it as a balanced chemical equation. If it is not, we have to balance that. For balancing, we have to use the coefficient terms only. So now, if I consider this reaction, now I am going to say how to explain or how to similarize the term of a mole concept with respect to this. Okay, so now see, that depends on stoichiometry. So what is that stoichiometry stands for? The measurement of elements, we call it as a stoichiometry. I repeat, the measurements of elements, we call it as a stoichiometry, and that mainly depends on the coefficient here. So here, how many CH4 we have? 1. Therefore, 1 mole of CH4. How many oxygens we have? 2. Therefore, 2 moles of oxygen, and 1 moles of carbon dioxide, and 2 moles of water. This is how the coefficients are considered as stoichiometry, and that is the measurement of elements, and based on that we can write a mole in this case. So now the question arises, 1 mole of CH4, 1 mole of methane has how many grams? Methane is a compound, molecular mass, and if you calculate that, you are going to get 16. So 1 mole of methane has a 16 grams. 1 mole of methane has how many particles? 6.022 into 10 to the 23 molecules we have. 1 mole of methane has how many volume? Okay, and 1 mole has a 22.4 liters or 22,400 milliliters. This is how you need to consider. So now if you consider one more, that is 2 oxygen. 1 mole of oxygen, and since 2 moles we have, and 2 into the molar mass of oxygen, that is 32, you have to multiply it by 2. So similarly we can calculate carbon dioxide and water. What is the meaning of this reaction is 1 mole of methane reacts with the 2 moles of oxygen, we are going to get 1 mole of carbon dioxide and 2 moles of H2O, and here that depends on the given whether we need to calculate in terms of mass or particles, or one more is volume. And for this one, you need to apply the different applications for this one, and for that one I repeat, the first 3 in general what I have written, if you know that, we can apply to n kind of problems like this, and that is all about the concept of mole. Remember, the amount of a substance can be represented by mole, and mole can be represented in 3 different manner: mass, particles and volume. I have given in general and I explained with one example, and a number of examples you can solve on your own. Now we'll see the one more heading, that is percentage composition. Percentage composition, and we know that one, the compounds are formed by elements, and these elements are in fixed ratio. We know this according to the law of definite proportion. And now here we'll see what would be the percentage composition of element, in what percentage the particular element is present in a given compound, like that. So we have a formula to calculate that percentage composition of an element. Here we are calculating percentage of each and every element in a compound. The formula is mass of element. Remember, mass of element divided by molar mass of the compound. The molar mass of the compound in terms of grams into 100 percentage, and if you use this formula, we can calculate the percentage composition of any element in a compound. One example I am going to solve here. Calculate a percentage composition of hydrogen and oxygen in water. So now see, water, the formula will be H2O, and water contains hydrogen and oxygen. And now the question is, in what percent of hydrogen is present and what would be the percentage of oxygen in water? How to calculate that? And that calculation depends on this formula. Okay, so first what we have to do is, you have to see which given compound we have. What is that? Water is the given compound. You have to calculate the molar mass of that. So I am going to write here molar mass of water. So what is the molar mass of water? And we know that one, molar mass, formula mass, molecular mass, different ways of representing, but the calculation is the same. Sum of atomic masses here. Hydrogen is 1, we have 2 hydrogens plus oxygen. The atomic mass is 16, and totally you are going to get 18 grams. So what is that 18 grams? 18 grams is the molar mass of water. So okay, first you have to calculate the molar mass, and now we'll see. Percentage of hydrogen we'll try to calculate first, and later one more element is oxygen. Therefore percentage of oxygen will calculate. Each and every element, you know, we have to calculate percentage of hydrogen and percentage of oxygen. Now see, percentage of hydrogen, what is the formula? Mass of element divided by molar mass of compound into 100. Which element I considered? Hydrogen. So what is the mass of hydrogen? 2, H2 we have, isn't it? Divided by, next what we have? The molar mass of a compound. What is the molar mass? That will be 18, and into what we have to consider? 100 we have to consider. This is how you have to apply the formula. The second one is percentage composition of oxygen. Okay, and how many oxygen we have here? In case of oxygen, O, and that is 16. Okay, divided by 18. 16 is the mass of oxygen element. Okay, and 18 will be the molar mass into what we have? 100 here. And if you calculate these two, you will be getting in terms of a percentage, and this is a well-known example, and therefore the value is 11.11 percentage, and for this one 88.88 percentage you are going to get. And this is how one can calculate the percentage of element present in a given compound. Okay, and that we call it as the percentage composition. And try to remember this formula, and you can apply it for n number of examples for that. And here I consider one very simple example, that is water. Okay, and if we have 3 elements in a compound, one example I am going to consider C2H5OH, that is ethyl alcohol or ethanol. And if you want to calculate the percentage composition of each and every element in this compound, and you need to look here. So carbon is one element, hydrogen is one element, oxygen is one element. We have 3 different elements here, and you need to calculate the percentage composition of carbon, hydrogen, oxygen. And before calculating the percentage composition of each and every element, first you have to calculate the molar mass of ethanol. And I told you how to calculate molar mass, sum of atomic masses here. Apply the same principle, you are going to get the percentage composition. Similarly, n number of examples we can solve using the percentage composition. If you know the formula, that is percentage composition of element in a compound is equals to mass of element divided by molar mass of compound into 100. Since we are going to calculate percentage, therefore we need to keep the answer in terms of a percentage only, and that is how the percentage composition problems can be calculated. Now we'll look over one more kind of problematic theory, and the word I use here is empirical formula, and one more is a molecular formula. Empirical formula, molecular formula. So what is that? Let me explain with one simple example. C6H12O6, and I hope you know this is the molecular formula of glucose. C6 H12O6. Molecular formula, we know what is that molecular formula and how to calculate molecular formula of glucose. But here we have three different elements, carbon, hydrogen and oxygen. So 6 carbons we have, 12 hydrogen and 6 oxygens we have. In this case, if you consider the simplest ratio, what is the simplest ratio of that one? Carbon 1, hydrogen 2, oxygen is 1, 6, 12, 6. If you consider the simplest ratio, or if you divide these numbers divided by the common, that is 6, and you are going to get 1 to 1, isn't it? So this we call it as a molecular formula, whereas the simplest ratio, this we call it as the empirical formula. Empirical formula is different and molecular formula is different. Remember, empirical formula is nothing but simplest whole number ratio between atoms. Simplest whole number ratio. Here carbon, hydrogen, oxygen are in the ratio 1:2:1. That is the simplest whole number ratio. Whereas the molecular formula, actual number of atoms of an element, actual number, how many atoms we have? 6:12:6, and that we call it as a molecular formula. Molecular formula is different and empirical formula is different, and we have a relation that relates these two, and the formula is molecular formula is equals to empirical formula into n we have. And what is that n? And n can be calculated by the ratio of molecular mass divided by empirical formula mass. So these two formula you should know, and that is the concept about the empirical formula and molecular formula. And the question is this: why we need to know the difference between empirical formula and molecular formula? Since what happens here, sometimes they may give the percentage composition of elements and what is the ratio of the elements, and finally we are going to get they ask what would be the molecular formula, what would be the empirical formula. So such kind of problems here. So these are the frequently used formula what you should know. So try to know this formula, molecular formula equals empirical formula into n, and one more is where n stands for molecular mass divided by empirical formula mass, and that is about the mole concept and the percentage composition and the molecular formula and empirical formula. We'll see one example for the relationship between molecular formula and empirical formula. So here I considered one NCERT example. Let me read the example. A compound contains 4.07% hydrogen, 24.27% carbon and 71.65% chlorine. A compound has three different elements. One is hydrogen, one more is carbon, and one more is chlorine, and the percentage composition of each element has been given. Its molar mass is 98.96 grams per mole. The compound molar mass they have given, that is 98.96 grams per mole. And what are its empirical formula and molecular formula? So they have given three different elements percentage composition, and they have given the molar mass of the compound, but we need to calculate the empirical formula and molecular formula. And how to solve this example? So first, to solve the problems of molecular formula and empirical formula, we need to draw a table like this, and that will help to calculate the empirical formula. And once we get empirical formula, easily we can go with the molecular formula. So what we have in the table? So we have to construct a table like this. In the first column we need to mention elements, second column the percentage of the each and every element, and atomic mass in the third column, number of atoms in the fourth column, and the simplest ratio in the last column. So this 5 different columns we need to construct like this. And now we'll go on the solving, okay? And after constructing the table, so let me help you how to get the empirical formula. In the first column what we have? Elements. So from the given data, how many elements are there we need to calculate. So the first element is hydrogen, okay? Second element is carbon, and the third element is chlorine. So elements what we have, and we need to write that. If you have one more element, we just extend that. If you have only 2 elements, construct only 2 rows like this. Then what would be the percentage of respective elements we are supposed to write in the second column by observing the given data in the problem we have. So hydrogen percentage is, what is that? 4.07, right? And carbon percentage is 24.27, right? And chlorine percentage is 71.65. So there is no big deal in the drawing the column, the first one and second one, because from reading the problem itself here we just write that one. Okay, the third column is what is that? Atomic mass. Atomic mass of the frequently used elements, we know that one. So what is the atomic mass of hydrogen? Atomic mass of hydrogen is 1. Okay, carbon, the atomic mass of carbon is 12, and chlorine, the atomic mass is 35.5. you need to remember that one. Okay, and 1 is the atomic mass of hydrogen, 12 atomic mass of carbon, 35.5 is the atomic mass of chlorine. So this you should know, the atomic mass here. The fourth column, what we have, number of atoms we have. So what we have to do that? So if you want to calculate number of atoms, and what we have to do is, you have to take the ratio of percentage composition and atomic mass. You have to divide these numbers by these numbers. So first one I am going to calculate. First one is for hydrogen. So now we'll see number of atoms of hydrogen. So what is the percentage composition? 4.07. What is the atomic mass? 1. We have to take the ratio of that, and if you divide this, you are going to get 4.07. that is the number of atoms. Nearly equal also we can write, and if you write nearly equal, that will be 4. Okay, and the next one, what is that? Is for the carbon, and we have to take the ratio of that, and that is 24.27 divided by 12, and we need to calculate. Of course you can write nearly equal, and using simple calculator you need to calculate this, and for this one we are going to get the answer as 2.02. Okay, and for the last one, what is that? For the chlorine, here 35.5 divided by, and you need to take the ratio of percentage versus atomic mass. Okay, I have written little bit the wrong, so therefore 71.65 divided by 35.5, and if you take the ratio of that one, and exactly we will be getting a 2.01. so exact value I have written using the simple calculator, or you can write a nearly equal value also. So this is the method how to calculate the number of atoms. So try to know the fourth column, that is number of atoms, can be calculated by taking the ratio of percentage and atomic mass, and know that one. If you divide 4.01 by 1, okay, the answer you are supposed to write. So similarly this division and this division, the answer you can write. You can write a nearly equal value, or you can write the exact value also, that doesn't matter much. So the last column is very important one. So what is that one? Simplest ratio. So how to calculate the simplest ratio for that one? So simplest ratio, you need to see the number of atoms, that is nothing but previous column, you need to see. Here we have 4.07, 2.02, 2.01. So out of these three, which one is the least? Okay, you need to consider, and one can easily guess, and among these three, 2.01 is the least, and you have to divide each and every number by the least number, that is 2.01. so what we have here? We have 4.07 divided by the least is 2.01. similarly 2.02 divided by the least is 2.01. and here the last one is 2.01 divided by what? Actually 2.01. okay, the least number has to be divided in this case. So now in this case you can write the nearly equal number I am going to write, because simplest ratio if you need. Okay, and one can easily guess, 4.07 divided by 2.01, the simplest ratio, the nearly equal 2 point something, nearly equal to you are going to get, and in this case we are going to get, and in this case we are going to get what? Actually 1. and what is the simplest ratio we got? 2:1:1, the simplest ratio we got. Okay, and this is how we need to construct the table, and we have to write the respective values in the column, and the last column is very important one. Okay, the simplest ratio, and take care of calculating number of atoms in this case. So now after drawing the table, we'll calculate what will be the empirical formula. So from the table we are going to get empirical formula. Okay, and if you recall the meaning of empirical formula, what I told you, that is the simplest whole number ratio of atoms. Okay, and what are the different atoms or we have hydrogen, carbon and chlorine. I am going to write here hydrogen, carbon and chlorine. Okay, and you can write however you want here. You can write carbon first, hydrogen second and chlorine last. Okay, that doesn't matter much. And the simplest formula, the empirical formula, I have written the elements. So what is the simplest ratio? 2:1:2. Hydrogen is 2. See here, the 2 simplest ratio is for the hydrogen. For the carbon it is 1 and chlorine is also 1. So empirical formula can be calculated using this table only, and that is very important one, simplest whole number ratio, and this is how empirical formula can be used. So now if you know the empirical formula, and now we'll see how we can calculate the empirical formula, and one more is molecular formula. So now next I am going to calculate empirical formula mass. Empirical formula mass I am going to calculate. Empirical formula mass. This is empirical formula and I am going to calculate empirical formula mass. If we have molecular formula, we can calculate molecular mass. The same method we will calculate empirical formula mass. Hydrogen atomic mass is 1. How many hydrogens we have? 2. Okay. Carbon, what is that? 1 we have, that is 12, and chlorine, that is 35.5. Okay, and if you add this one, you are going to get empirical formula mass. 2 plus 12, 14, 14 plus 35.5, I think 49.5 you are going to get. So that 49.5 grams, that is empirical formula mass. Now we'll calculate what is the value of N. I told you already what is the formula N. So what is the formula? N can be calculated by molar mass, or you can say molecular mass divided by empirical formula mass. Empirical formula mass. So if you take the ratio of that one, molar mass and empirical formula mass, and you are going to get the value. Molar mass, that is given in the problem, that is 98.96. So 98.96 divided by empirical formula mass we calculated before, that is 49.5. So empirical formula mass is required. Therefore we calculate the empirical formula first and empirical formula and the last. And if you take the ratio of this one, and actually it is the exact value is 1.99, and nearly equal I am going to write 2. So therefore we got the value of N, that is 2. So finally we are interested in molecular formula, and the formula I told you that already, that is molecular formula is equals to, molecular formula is equals to empirical formula into N we have here. So what is the empirical formula we got? So here we have empirical formula, that is H2, okay, and C1 and Cl1 we have, and N, what is the value of N? And it is 2, and we have to multiply that 2 with the simplest whole number ratio, and we are going to get what actually H4C2Cl2 will be the formula. Okay, and that is how we got the molecular formula. How these are interrelated? Molecular formula will depend on empirical formula and N, isn't it? And N will depend on molar mass and empirical formula mass. Remember, molar mass usually they will give in the problem. Empirical formula mass we need, and if you want empirical formula mass, we need empirical formula, and if you want empirical formula, the table is a very important one. So this is how we can calculate empirical formula and molecular formula. And let me repeat that one. In the problem they ask usually the empirical formula and molecular formula. They may give any element with the percentage composition, and usually they will mention the molar mass of the whole compound, and you need to construct a table. Okay, and number of atoms and simplest ratio is the very important thing you need to calculate. And once if you get the simplest ratio, you need to calculate empirical formula. If you get empirical formula, calculate empirical formula mass, and then you calculate value of n, and then apply the formula, then you are going to get the molecular formula. And the difference between that, we know that one empirical formula simplest whole number ratio, whereas a molecular formula actual number of atoms. So what we have, you are going to consider, and you can write any way you want. You can write a C2H4Cl2 also the same thing, but remember and how to draw the table, and this taking the simplest ratio is important one. And if you get any wrong simplest ratio, the entire example will be wrong. Take care of drawing the correct table, and that is how we calculate the problems based on empirical formula and molecular formula. One more term I am going to explain here, that is the limiting reagent. Okay, so we'll see that one. Two reactants will combine, and we are going to get a product. That is how, you know, the combination reaction what we have. Sometimes what happens, one reagent will be in a very little amount and one reagent will be in more amount. Okay, that depends on the coefficients, or you can say stoichiometry of the elements. Okay, and the smaller reagent, the minimum amount reagent, that is consumed in the reaction, whereas excess reagent, the amount of the limited reagent or the minimum reagent what we have, the same amount will be consumed and some extra amount of the reagent will be present, and that we call it as excess reagent here. So limiting reagent is nothing but the reagent which is completely consumed, that is the one with the small amount, the reagent which is completely consumed during the reaction and limits the amount of a product formed. Once the limiting reagent is consumed and one more reactant or one more reagent what we have, that is left as it is, that we call it as excess reagent. And the limiting reagent is very important to guess the product formed, and that reagent we call it as the limiting reagent. Reactant which is completely consumed during the reaction and limits the amount of a product formed, and that is how limiting reagent is going to be defined. Now we'll see the last part, that is concentration terms. Amount of solute present in a given solution, we call it as concentration, and the concentration of a solution can be represented in a different forms. And for our syllabus we have 4 different forms of measuring the concentration of solution. One is mass percent, second one is mole fraction, third one is molarity, and the last one is molality. So now we'll see how we can explain the terms involved, the concentration terms. So first one I am going to talk about, that is a mass percent. In terms of percent, we are going to measure the amount of a solute present in a given solution. So what is the formula we need to consider? Mass percentage is equals to mass of solute divided by mass of solution into 100. Once you know that, when a solute reacts with the solvent, we are going to get a solution. So mass of solute, the amount, the solute is nothing but the component which is present in small amount, we call it as solute. The component which is present in large amount, we call it as solvent. When these two will combine, we are going to get a solution. So the small amount, that is solute, if we need to consider the mass of that, and mass of solution, and if you multiply it by 100, we are going to get the mass percentage. The second one is mole fraction. Sometimes we represent with the terms. So mass percent we can represent W divided by W percentage. The mole fraction, the symbol for mole fraction is a small x. Try to know that one. Small x is a symbol for mole fraction. So what is the formula we have, we'll see. And before that, we'll see what actually Na and Nb stands for. Here I considered A and B are the two components. So A and B are the two components. If I considered Na, where N stands for number of moles, where a small n stands for number of moles, and Na number of moles of A, Nb number of moles of B. So first we need to consider what is that N stands for. N stands for number of moles, and for A, Na, for B, Nb we write. So how we can write the mole fraction of A and mole fraction of B? I told you that one mole fraction can be represented in the form of X here. So mole fraction of A, what I should write here? Xa. And the formula is Xa is equals to Na divided by Na plus Nb. So we have the component A, and you have to consider the same same number of moles of A divided by total number of moles of the component. A and B are the components, therefore Na plus Nb. What about the mole fraction of B? Xb is equals to the component we have B, therefore in the numerator we need to write number of moles of B divided by total number of moles of A and B, and that is how this is a mole fraction of A and this is a mole fraction of B. We can calculate. Mole fraction is represented by X. So in general, the mole fraction can be defined as the ratio of number of moles of a particular component to number of moles of all components present. In general we can say, and two components I considered, therefore I have written XA and XB. The third one we'll see, that is the molarity. Okay, molarity can be represented by capital M. Remember that one, molarity, capital M. So what is the meaning of that one, molarity? Molarity is defined as the ratio of number of moles of a solute over volume of a solution in a liter. In simple sense, we can say number of moles of solute present in 1 liter of a solution, we call it as a molarity. The main thing is, remember, we are going to consider number of moles of a solute. Solute amount can be represented by number of moles, and present in 1 liter of a solution, this is the very important one. In a molarity we are going to consider volume, and 1 liter of a solution volume we are going to consider, and that is a molarity. Contrary, molality we have one more, and that is represented by small m. Know the difference? Capital M molarity, small m molality. And if you see the formula what I have written, molality, number of moles of solute, the same thing, amount of a solute present in mass of a solvent in kg. Here we considered mass, that is in 1 kg of solvent of mass, how many number of moles of solute we have, and that is a molality, and this is a molarity. Try to know the difference. In a molarity we consider volume, in a molality we consider mass. This is the main difference. In a molarity 1 liter, why? Because we considered a volume of solution. 1 liter of solution. Here we considered mass of a solvent. Here, see here, this is the solution we have, and here we have a solvent, and here usually 1 liter we considered, and usually 1 kg we considered. That is the main difference between molarity and molality. We can generate the formula to calculate that. M is equals to capital M molarity, W2 divided by M2 into 1000 divided by V, where W stands for weight, M stands for molar mass. W2 weight of solute, M2 molar mass of solute, 1000 divided by V. V is nothing but the volume of a solution in liters. Similarly, small m can be represented as W2 divided by M2 into 1000 divided by W1, where W1 stands for the weight or mass of a solvent here. In general, 1 I represent it as for solvent and 2 for a solute here, and that is how we can calculate the problems based on that. The main difference is molarity V we have, since we calculate volume. Molality W1 we have, that is the molar mass of the solvent what we have. Okay, and that is about the different concentration terms what we have, and the problems are very simple based on that. And if you know the formula, you can calculate some problems based on that. One example I am going to give you here. In case of a mass percentage, okay, let us assume 2 grams of a solute. 2 grams of a solute, we are going to add in 80 grams of a solvent here. This is a solute, see here, this is a solute, 2 grams, and 18 will be the solvent. Let us assume that 2 grams of solute is going to be dissolved in 18 grams of a solvent. And what would be the mass percentage, and how to solve that one? Mass of solute, what is the mass of solute? That will be the 2 divided by what we have, mass of a solution. Remember, solution we have, and not a solvent here. Solution contains both a solute and solvent. So mass of a solution, that is 2 is a solute and 18 is a solvent, and into 18, this is how we need to consider. And if you simplify further, 2 divided by 20 into 100 you are going to get. Sorry, here this is in terms of a percentage, therefore 100 you are supposed to consider, and I hope you are going to get the answer as 10%. So 10% is the mass percent for this example what I considered. Similarly, we can solve some other problems based on that also, and one on molarity I am going to consider. Let us assume 4 grams of NaOH, sodium hydroxide. 4 grams of NaOH is dissolved in a water to make the solution as 250 ml. 4 grams of NaH and the volume we have 250 ml. What would be the molarity? The formula we have here, that is capital M. Molarity is equals to W2. What is W2? The weight of a solute. Which one is solute? 4 grams we are adding, therefore 4 divided by M2. What is M2? Molar mass of solute. Molar mass of solute. Solute is NaOH, sodium hydroxide. The molar mass you need to remember, and we know how to calculate molar mass of NaOH. Okay, sum of atomic masses here. Sodium, the molar mass is 23, atomic number is 11, atomic mass will be 23. Oxygen, okay, it is 16, and we have 1 for the hydrogen. And the answer will be what actually 23 plus 16, that is 40 you are going to get, and divided by 40 into 1000 divided by V is nothing but the volume of solution. What is the volume we have? 250 volume we have. And if you simplify this one and 250, here you are going to get 4, and the answer will be 0.4 capital M. That will be 0.4 molarity you are going to get. This is how one example I consider to solve the problems based on that. Similarly, if you have molality, you need to consider W1, that is the weight of a solvent here. And in case of a mole fraction, of course they will mention the number of moles of A and number of moles of B also here. And out of curiosity I am going to write one thing, and do you guess what would be the value of XA plus XB? What is XA? Mole fraction of A. What is XB? Mole fraction of B. And if you add that one, and I hope you are going to get answer as 1. Why? Because we are supposed to add these two. LCM will be Na plus Nb, and in the numerator also you are going to get Na plus Nb. Get cancels, you are going to get 1 actually. And if you want to know the value of XA, 1 minus XB you need to calculate. And if you want to know 1xB and 1 minus XA you are supposed to calculate. This is how some rearrangement we can do in case of mole fraction. And all these are the concentration terms: mass percent, mole fraction, molarity and molality. And one example I have given, and in all the concepts what I explained I have given one example only, and you can refer NCERT textbook and you can solve some other examples also. And that is all about the session number 3, and that will be the end of the chapter, Some Basic Concepts of Chemistry. Thanks for watching.